Water, known chemically as H2O. Water is an inorganic, transparent, tasteless, odorless, and nearly colorless chemical substance, which is the main constituent of Earth's hydrosphere and the fluids of all known living organisms. It is vital for all known forms of life, even though it provides no calories or organic nutrients. But it's not always clean. All natural waters contain some foreign substances or impurities, usually in small amounts. The water in the river, in a well, or in your tap at home is not just pure, high-quality H2O. It also contains some amounts of solid and soluble substances such as sand or other debris that can usually be filtered out, and some soluble substances that you most often cannot see and that cannot be filtered out. These substances can be inorganic or organic. In other words, they can be living or not living. They can be ionized, electrically charged, or not. The substances in your water could also be gases like carbon dioxide. So why treat water? Well, specifically here at SRS, we treat water to minimize corrosion, minimize radiation levels, and minimize fouling of heat transfer surfaces. Now, we'll cover the subject of corrosion in a lot more detail in the next module, but for now, just remember that impurities in water can cause corrosion of systems and components it comes in contact with. And I don't know if you've noticed, but at SRS, a lot of our systems and components we use to store and transfer waste are old and made of metal and exposed to the elements, so we have to do our best to prevent corrosion, which can lead to system or component failure, and that could potentially lead to some bad stuff getting leaked to the environment. Now, because we're at a nuclear waste site, there is a potential for some of the impurities in water to pick up some radiation. So another reason we treat water is to minimize radiation levels. If this water is left untreated, it could potentially be carried to all parts of a system, creating a personnel radiation hazard. This picture, you may recall from another course, is a tube and shell heat exchanger. This is the way it looks brand new. This is what it looks like after being subjected to a phenomenon known as fouling. The fouling of heat exchangers may be defined as the accumulation of unwanted impurities on heat transfer surfaces. These impurities decrease heat transfer capabilities. So that's another reason we treat water here at SRS, to minimize fouling on heat transfer surfaces. Now we'll discuss the three methods we use to treat water here at SRS: deaeration, filtration, and ion exchange. Deaeration is used to remove dissolved gases from the water. The way it works is water is placed in a vented tank and heated to a slow boil. Now this boiling strips the gases from the water. Remember when we talked about how in a liquid gas solution, when you heat it, the gases come out of solution? Well, the same thing applies. These gases go through a condenser which cools it slightly, and this is to limit the loss of water vapor before being vented to the atmosphere. Filtration. Now, we've probably all experienced using some kinds of filters in our lives: coffee filters, tea bags, your air conditioner filter. A filter's job is to remove suspended or non-dissolved solids from the water. When we process water, the filtration process is usually one of the first processes the water goes through. Here are the 5 types of filtration media you'll need to know for this course. The final method of treating water we're going to talk about is called ion exchange. Now, while filters get rid of suspended or undissolved solids, ion exchange gets rid of dissolved solids. Ion exchange is a method where we purify water by removing undesirable ions and replacing them with desired ones. So what are some of these undesirable ions or impurities we're trying to get rid of? All natural waters contain, in various concentrations, dissolved salts, which come from various sources. These salts dissociate in water to form charged ions. Positively charged ions are called cations, and negatively charged ions are called anions. So these are two new terms you need to know. This chart shows some of the ions that may be present in water. To determine which of these ions are present, we take samples and send them to a lab for analysis. Some of these ions, like calcium, iron, and magnesium, can make the water hard. I'm sure you've heard the term hard water. These ionic impurities can cause limescale buildup, which can seriously affect the reliability and operating efficiency of process systems at SRS, and can also degrade components in your home. The devices used to exchange these undesirable ions with desired ions are called deionizers, demineralizers, and ion exchangers. We're going to go with the term ion exchanger. Sometimes you'll see ion exchangers abbreviated as IX. So the purpose of an ion exchanger is to remove unwanted ions and replace them with desired ones. We've already seen examples of unwanted ions, so what are the desired ones? Well, in most cases, these would be hydrogen ions and hydroxide ions. Why? Because if you put these two ions together, what do you get? Think about it. H2O. And in some cases, other ions may be desirable, such as lithium, sodium, or maybe chloride. We're now going to talk about the design and construction of a basic ion exchanger and explain how one works. First of all, you have a metal tank filled with tiny resin beads, which we'll talk about later. You have an inlet at the top where the water to be purified, called the influent, comes in. The water gravity flows across and mingles with these beads. Now note you have a bed of anion beads and a bed of cation beads. During this process, the ions are exchanged and the water coming out, the effluent, is purified. Also on these ion exchangers, you have screens on the bottom and top called upper and lower retention screens. These keep the beads from escaping. You also have connections at the bottom and the top where you can load the new beads or get rid of the old ones. So that's the basic design and construction of an ion exchanger. Okay, the resin beads. Okay, these resin beads are very, very small, so each resin bed can have over 1 million of these beads. Okay, the picture on the left shows what they look like to the naked eye, and the other two photos show them under a microscope. Now, these beads belong to a group of compounds called polymers. Now, if you want more information on polymers, feel free to Google, but for the purposes of this course, just remember that polymers are any of a class of natural or synthetic substances composed of very large molecules, large strings of molecules. The natural ones are things like proteins and amino acids, but the resin beads are synthetic or man-made. In fact, there's a plant in Augusta you may be familiar with that produces the same type of polymers used in certain resins. These beads are insoluble in water, acids and bases, so they won't dissolve when they're put through the system, through the process, although they do have some limitations, as we'll see later. So these beads are custom made for the ion exchange process. To understand how this process works, let's imagine each bead being a golf ball. Imagine each dimple on a ball as a site where ion exchange can occur. In reality, each bead has several hundreds of these sites. First, we'll talk about the anion resin beads. Remember, anion resin beads are designed to exchange negatively charged ions. And the most common desirable ion that we want to exchange the undesirable ions with is hydroxide. So here I superimpose a few of these dimples with OH negative or hydroxide just to illustrate that each of these sites has these ions attached. The cation resin beads are designed to exchange positively charged ions, and the most common desirable positive ion, as we said earlier, is the hydrogen ion. So here I superimpose a few of these dimples with H+ or hydrogen ions. Now that we have an idea of what the beads kind of look like, we'll now discuss how the process works. Ion exchange works because of the concept called relative ion affinity. The word affinity just means likability or attraction. So here we're talking about the relative attraction between a resin bead and a particular ion. Here's a table of relative ion affinities to resin of some common ions that may be found in water. The higher up you go on the table, the stronger the affinity or attraction. So take a minute to look at this list and notice where the cation hydrogen and the anion hydroxide are in their respective columns. Notice they are near the bottom, meaning that while the resin bead has somewhat of an affinity for them, the beads are attracted more to any ion listed above them. So the idea is, initially the resin bead has an ion attached to it that it likes, kinda, like the hydrogen or hydroxide. But then along comes an ion that the resin bead likes better or has a higher relative ion affinity for, and the resin bead grabs the ion it likes more and dumps the one it likes less, and the released ion becomes part of the effluent stream. As a result, the undesirable ions have been removed or exchanged for desirable ones, and we should have purified water coming out. Here's an example. What if we have some water that has too much calcium in it? We use an ion exchanger with a cation resin bed with hydrogen attached to the beads, because we know from our relative ion affinity list, the beads will dump the hydrogen and grab the calcium when it comes through. So in this animation, the black dots attached to the beads represent the hydrogen ions. As the calcium water comes through, the calcium ions, represented by the red dots, replace the hydrogen ions on the beads, and the beads drop the hydrogen and grab the calcium. Now, what if you wanted to replace the calcium with sodium? This is often done to soften water. You would just use a cation resin bed, and instead of using beads with hydrogen attached, you use beads with sodium ions attached. Checking our relative ion affinity table, we see sodium is near the bottom of the list, so the beads like calcium more, so we expect the beads to discard the sodium into the effluent stream and grab the calcium. Here's a little more complicated example, but the same concept. This time we want to get the salt out of water. We know that an aqueous saline solution contains sodium cations and chloride anions. So to remove them both, we need a mixed resin containing cations, in this case hydrogen, and anions, the hydroxide. Now we have an equation that explains the ion exchange process, and you need to become familiar with this format. And this first equation describes the process of exchanging the sodium for the hydrogen. The H is the hydrogen and R is a resin bead. So H-R represents the resin bead with the hydrogen attached. We add the water with the sodium, so that represents the influence stream of water with the sodium. And we see on the product side, the sodium is now attached to the resin bead, R, and the hydrogen goes on its merry way into the effluent stream. And this equation describes the anion exchange process. Once again, the chloride ions are attached to the beads, the hydroxide is in the effluent water, the salt has been removed. Okay, review time. Remember the definitions of acids and bases? Acids dissociate in water and form hydrogen ions, and bases dissociate in water and produce hydroxide ions. So the more hydrogen ions in a solution, the more acidic it is, and the more hydroxide ions in a solution, the more basic it is. Now I'm sure you also remember the concept of pH. The pH of acids is below 7. The pH of bases is above 7. Low pH, more acidic. High pH, more basic. Therefore, if you want to decrease the pH of a treated solution, and that is slow down the rate of pH increase, you use a hydrogen cation resin to make it more acidic. And an anion resin, if you have to use an anion resin, use something other than an OH negative, because if you add OH negative hydroxide, it will drive up the pH. And here you don't want to do that. So if you want to bring the pH down, use hydrogen cation resin and anything but OH negative. Conversely, if you want to raise the pH, make it more basic, or slow the rate of pH decrease. It's going down too fast. You want to keep it from going down. You use an OH negative hydroxide anion bed and anything but a hydrogen cation bed. So what can go wrong? There are 5 ion exchanger malfunctions we're going to talk about. They are resin channeling, resin breakthrough and exhaustion, resin overheating, resin fines, and organic fouling. Resin channeling is when a flow channel or channels are formed from the inlet to the outlet, allowing a direct flow of water through the exchanger. This is normally caused by excessive flow velocity, but can also be caused by the ion exchanger being overfilled or not filled properly. As a result, the water has minimal contact with the beads, and for the ion exchanger to do its job effectively, we want the water to have maximum contact with the beads. Resin breakthrough and exhaustion sound like two separate malfunctions, but they are related, and you'll see why in a moment. Before you send the dirty water through the ion exchanger, you've taken a sample so you have an idea what kind of ions are in this influence stream that you want to take out. At the outlet, you take another sample to confirm that the ion exchanger is doing its job and the unwanted ions have indeed been removed. If during this sampling of the effluent stream at the outlet, you find some of these unwanted ions are still present, we say that resin breakthrough has occurred. Resin breakthrough is when some unwanted ions break through to the other side, if you will. In other words, the ion exchanger isn't doing its job. Now, this can be caused by several things. Resin channeling, like we talked about earlier, or it could just be that the beads are old and all the exchange sites have been exhausted. All the exchange capacity of the resin has been used. In this case, the beads can be regenerated, which we'll talk about later, or simply replaced. So, resin breakthrough, unwanted ions breaking through, can be caused by resin exhaustion, but remember, could also be caused by resin channeling or some other malfunction we'll talk about that would keep the exchanger from doing its job. Now, the resin beads can withstand a lot of heat, but there is a limit. Now, you don't need to know what that temperature is, but you just need to know that at high temperatures, the beads can decompose. And the facilities that send water to our water treatment facility at ETP know this, and they ensure the water they send is well below this limit. The beads smell like dead fish when they overheat. And when this happens, they have to be replaced. They can't be regenerated. Resin fines. Expansion and contraction causes eventual deterioration of the beads. And when the beads get old, they can dry up. In these cases, they can crack into tiny pieces, and these pieces can clog the system or release undesirable ions. And these are called resin fines. Organic fouling. This is when carbon compounds, organic compounds like oil and grease, get into the exchanger and clog the pores, if you will. You want to make sure the water is free of these organic compounds before it goes through the ion exchanger. So the one thing all these malfunctions have in common is they all cause decreased efficiency of the ion exchanger. So now that we know what these malfunctions are, how are we as operators to know when they are occurring? We have these things on our equipment called instrumentation and controls, and there's a whole course on that, so you'll get that later. But on the ion exchangers, we have instrumentation and controls that will alert you to trouble once you get familiar with the indications. The first one we'll talk about is conductivity. Now, pure water does not conduct electricity. It's the ions in the water that create the conductivity. So we have instruments that measure conductivity on a continuous basis. Any increase could indicate unwanted ions in the effluent stream and that the ion exchanger isn't doing its job. And as an operator, knowing all the possible malfunctions we discussed, you can then investigate why. The ion exchangers have temperature instrumentation to monitor temperature to ensure the ion exchanger doesn't overheat. It also has flow gauges to monitor the flow rate. Remember, excessive flow rate can cause channeling. But low flow may also be troublesome because the ion exchanger isn't operating at maximum efficiency when you have too low a flow. Differential pressure is also measured. You'll get more about differential pressure later. But for now, just remember High differential pressure is an indication of pluggage. As an operator, you'll be responsible for monitoring all of these and possibly more parameters if assigned to this particular watch station. Also, as mentioned earlier, routine sampling is done to alert operators of abnormal conditions and to measure performance. The last topic to be discussed is resin regeneration. Now, as we talked about before, when the resins are exhausted, you can either replace them or regenerate them. That is, bring them back to the fresh state, the original state, and start over again. For example, here's an example of a type of ion exchanger known as a water softener. You may have one of those in your house. It originally has sodium beads because sodium softens water. In this case, the water softener replaced the calcium ions found in the water with sodium. The ion exchanger has finally exhausted all the sodium sites on the beads, so now these are calcium beads. This bed can be regenerated with sodium ions simply by running a sodium chloride solution over them as shown.